Okay, physics students. So what we're going to do is we're going to start talking about quantum physics, which is a really interesting part of the course. And as I've alluded to in class, what we're going to do is we're going to kind of turn upside down a lot of the ideas that we've learned about physics so far over the past year and a half of the course. Not that those ideas are necessarily irrelevant or wrong, it's just now we're going to realize that a lot of the things we thought were true about physics and physical phenomenon are not true in every single situation. So this is a really intriguing topic. And the first thing I want to do before I start talking about the photoelectric effect is just to simply talk about electromagnetic radiation. We've talked a little bit about this in class already, but you need to have at least a rudimentary understanding of what E&M radiation is in order to understand the photoelectric effect and especially how the photon works. Okay, so this whole idea of electromagnetism, okay, it manifests itself in the form of electromagnetic radiation, and I have my definition here is that E&M radiation is a form of energy released in E&M processes. That seems like kind of a cop-out, but that's really the best way to put it. Really what this is this is a wave, and they're synchronized waves or synchronized oscillations of electric and magnetic fields, and it kind of looks like this, okay? You've got this GIF is in three-dimensional space. You have an alternating electric field and a magnetic field. The magnetic field is given by the blue color here, and the electric field is given by the red color, and the velocity is to the right. So all three of those quantities are orthogonal to one another. So here's maybe a little bit of a better diagram showing that orthogonality between them. Okay. And I just also want to mention that some of the processes that make E&M waves are AC currents, accelerating charges, and transitions of electrons across energy levels, among others. Okay, so again, all three of them are orthogonal, and we can treat them. We can treat the two waves as a set of transverse waves. So we've already studied waves, and remember all the properties of transverse waves would hold here. So there's a wavelength and a frequency and so forth. So here's another view of these waves kind of from the side at an angle. Okay, this radiation or these waves travel at 3 × 10⁸ meters per second in a vacuum, and of course we call this quantity lowercase c in physics. It's a very, very important quantity. Okay. These waves can be characterized by wavelength and frequency, as I talked about before, because they're transverse waves. And I just want to reiterate that light is electromagnetic radiation that it just so happens that we can see with our eyes. There's nothing really special about visible light, other than our eyes have evolved to see electromagnetic radiation in that particular band of the spectrum, which I'll show you in just a minute. The other weird thing about this radiation or these waves is that they also behave as a particle called a photon, which I'll talk about later. Okay, so again, we only see a very small part of the electromagnetic spectrum, and really that's from about 350 to 750 nanometers wavelength. Okay, so here are the approximate bands, and I say approximate bands because you see how one kind of bleeds into the other. The blue kind of bleeds into the green, which kind of fades into the yellow, which kind of fades into the orange. So there's no real sort of set edge to these bands. So these are kind of ballpark figures here. All right, if you go beyond the blue in wavelength, a shorter wavelength than blue, or a higher frequency, because frequency and wavelength are inversely related, you get ultraviolet. If you go above the red in wavelength or below the red in frequency, you get what's called infrared. And our eyes are attuned such that we can't see UV or IR, but they're there. Okay, our sun emits mostly in this band, which is why the sun appears to be kind of yellowish. And you guys are bathed in electromagnetic radiation of all frequencies constantly. Radio waves, visible, X-rays, microwaves, everything. Okay, so here's our wave equation relating frequency and lambda. Okay, just an idea of the wavelengths of visible light, comparing them. When you see the term micron, that's a micrometer, just so you guys know. That's short for micrometer. Okay, so the way that this chart is set up is we have increasing frequency as we go to the left, which means that this electromagnetic radiation on the left has the highest energy, okay, because E equals F lambda, E E equals HF, okay? So I have danger over here, gamma rays, X-rays, those kinds of waves can give you cancer. They can ionize your cells, okay? And in the IV, it's really important that you know the order of these regions and decreasing and increasing frequency and wavelength. And so don't worry about necessarily memorizing this right now. You will get an intuitive feel of where these bands fall as you start working with this electromagnetic spectrum. You'll be working with this for a long time in this class, okay? Okay. A couple of sources of electromagnetic spectrum regions, okay? This is kind of interesting to sort of compare, okay? So radio waves, so electrical oscillator circuits, electron tubes. These are we use radio waves to transmit information all the time, okay? Microwave radiation, well, besides ovens, which is the obvious thing that might come to your mind, turns out that the background radiation of the universe emits electromagnetic radiation in this region. Infrared, which is what we feel is heat. An example would be an electrical oscillator circuit. Or maybe hot objects, okay? Also, hot objects also emit in the visible part of the spectrum, and that's, of course, electron excitation. X-rays, an example of X-rays would be deceleration of high-speed electrons, and then gamma rays can come from nuclear decay. These are not the only sources for these particular regions of the spectrum, but it just gives you kind of a taste of where they come from, okay? Now, what's really cool is that in astrophysics, we use different parts of the electromagnetic spectrum to get information about images in space. So, for example, what astronomers do is they will take images of different features in the night sky, okay, at different bands or different wavelengths, and different features emerge in different wavelengths. So it's very, very interesting. So, for example, this is the Crab Nebula. And these are images taken from different regions of the spectrum. Okay, now hold on. You might be thinking, well, we can't see radio waves. How can we see this? So what has happened here is that the scientists have basically converted a radio wave sort of topographic map into a color topographic map that shows us the patterns of the radio waves. And of course, each of these colors here corresponds to a different frequency in that particular radio part of the E&M spectrum. Okay, so you can see it looks really, really different depending on which part of the spectrum you're filtering it through. So that's how we know so many things about distant galaxies and stars. And of course, I just want to remind you that A, B, and D, you cannot see. The Crab Nebula doesn't look like that with the naked eye. The Crab Nebula looks like this, but there's so much more to it because it's emitting in all the different parts of the spectrum. Okay. Okay. Now, I'm going to talk about, in particular now, something called the photoelectric effect, which was a really, really important and special revelation in physics. Basically, that's what led Einstein to develop his theory that the energy of one photon is equal to Planck's constant times the frequency of that photon. Okay, so it's kind of a difficult concept. So you're going to want to really pay attention and very, very closely and slowly watch this video as I walk through the logic of the photoelectric effect. Okay. Now, it turns out that there are certain kinds of surfaces, certain kinds of metallic surfaces, where if we hit those surfaces with electromagnetic radiation, electrons in the valence electrons of those atoms, okay, in the valence shells, can be kind of loosened by the energy in the incoming waves. And if they're loosened enough, these electrons can actually be emitted or kind of stripped off the outer shell of those atoms, okay. So in this diagram, I have the incoming electromagnetic radiation coming in, okay. Here are the waves right here. They come in and they hit these electrons, and again, if the electrons get enough energy to break free, they will go flying off into space, okay? Now, if they have enough energy to break free, they're going to have a high frequency because frequency is proportional to energy, okay? So they can be actually physically ejected, and they're called photoelectrons in this case. So photosurface, photoelectrons. This phenomenon is called the photoelectric effect, okay? It was first observed in the late 1800s, and here's a basic apparatus for a photoelectric effect. Okay, this was the first experimental evidence that light exists in discrete units called photons, which I'll talk about in the next video. So, at the same time, or at that time, the photoelectric effect could not be explained solely with the ideas of classical physics. This is why the photoelectric effect was so important, because it really turned things upside down and got scientists thinking of light not just as a wave, but as a particle. Okay, so basically, the photoelectric effect was evidence that light exists as a particle, as a photon, in addition to a wave. Okay, so here's the setup. All right, what you have is you have a circuit. It's actually not a closed circuit. Okay, you have a plate over here and a plate over here. Okay, and it's connected to a voltage source. Okay, and then you're shining light through what's called a phototube, an evacuated tube. That light hits a particular plate. And then what happens is, if those electrons are excited enough, they will actually fly off and they will shoot this gap over here. Okay. And they'll be sort of sucked up or stuck onto the positive collector plate. Now, my rationale when I walk through this with you, my plates are going to be differently aligned, negative and positive, but the physics is the same, and that's because my battery will be backwards from this one, and you'll see what I mean when I show you. Okay. So a photosurface can be lots of different kinds of metals. Typically, it's sodium, zinc, copper, platinum, etc. And so what you do in this particular diagram is you position it near a positively charged plate. Okay, the ejected photoelectrons shoot the gap between a negatively charged photosurface and the collector. Okay, the ammeter in the circuit records the current. Okay, I just want to point out that it's the valence electrons that are loosened from the metal plate and ejected. The waves actually then do work on the electrons because they transfer energy to them. And that's really important to think about that in those terms, that there's work done by the photons or by the waves on the electrons. If we know the current, then we know the number of electrons that shoot that gap, right? And of course, we would measure the current with the ammeter connected in series with the actual phototube. So since the amount of charge is quantized, the incoming energy must be quantized or discrete too, and I'll talk about this a little more later. Okay, it turns out that a couple of weird things happen. Okay, this is actually not so weird. The fact that the intensity of the light is proportional to the current. Okay, so remember, intensity is brightness, and current is what we call the photocurrent. Really not that surprising. Remember that current is the charge per unit time. Okay, and what we're going to do in our analysis here is we're going to assume that one electron is loosened per photon. Okay, so what I'm showing you in this little GIF right here is that is this relationship right here. I'm starting off at 100%, and as I decrease the intensity, you see how the current actually goes down, and that makes sense. Okay, now the fact that the current would go down when the intensity goes down, it's due to one of two things. Okay, the possibilities are as follow. Number one, more electrons could be emitted when the light is bright. Okay, or electrons could be moving faster from the surface when the light is bright. Think about that. Those are the only two possibilities if this equation right here for current is correct. Okay, so the question is which one is correct. Now, if you look at this PhET simulation, you can probably surmise that more electrons are being emitted when the light is bright. Can you tell that they're not moving faster from the surface when the light is bright? I'm going to prove that to you, and in fact, it's actually case number one that's true. Okay, now pretend like you don't know that. Okay, we need to determine the energy of the emitted electrons to find out which is the case, and that's what we're going to do. Okay, so in order to do this, what we would do is we would actually now connect a battery between the photosurface and the plate, and we're going to connect it backwards, and we're going to sort of play around with the voltage, the potential difference across that battery. Okay, all right, so in this case, it's as if there's no battery at all. Okay, and of course there's a current here. Okay, if you increase the voltage very slightly, what you would do, and when I say increase the voltage, I'm talking about increasing it with respect to how this battery is aligned. If I were to flip this battery around, it would be the opposite. Okay, but if I increase the voltage, basically what you do is you would help the electrons jump that gap or get across the gap, because the right plate would be positive and the left plate would be negative. Okay, so for example, this is an EMF of 1 volt, and you can see how it basically speeds up the electrons, because it's the positive plate. You can think about it, it kind of sucks them over to the right hand side. Notice that the current is the same though. Okay, if I really increase the potential difference, notice how the current still stays the same. This is very, very interesting. Okay, but in this case, in this case, I still have a positive and a negative. Notice how I have not changed the intensity at all. The current doesn't change no matter what the EMF in this case, in this particular setup. Okay, so The right side again would be positive and the left side would be negative if you increase the voltage the way that this battery is oriented. Okay, so the key is to not only connect the battery between the photosurface and the plate backwards, but you want to decrease the EMF as this is set up here. Okay, so eventually every electron will be repelled by the negative plate and return to the positive left side of the photosurface. Okay, so this is the setup that was being referred to in that particular diagram that I showed you before. Okay, so in other words, you're going to decrease the potential difference, which will decrease the current until the current equals 0. Notice that this is not, I'm not talking about Ohm's law where V equals IR anymore. Okay, we're actually not even talking about, we're not even going to consider the resistance of the circuit. All we're doing is we're trying to find that magical potential difference here such that every electron, not a single electron, barely doesn't make it to the collecting plate. That's really bad English, but you know what I mean. And this particular voltage is called the stopping voltage, and it's called V sub S in physics. Okay. Now, if I graph current against the voltage, all right, I get something like this. Okay. You can see that regardless of the intensity of the light, in this case, this is a graph, two different graphs for red light. Okay, red frequency. Doesn't matter what the intensity, what the brightness is, you still have the same stopping voltage. Now the graph is still the same shape, but the bright graph is a little bit higher than the dimmer graph. Okay, so again, intensity is proportional to current, and it's because more electrons are emitted when the light is bright. And I will prove this again to you in a different way later. And whether bright or not, light of the same frequency has the same stopping voltage. This is surprising due to the, according to the classical laws of physics, okay, which I'll talk about a little more in just a minute. Okay, now comparing red to blue. Okay, so if we have bright light, same intensity, blue and red, it turns out that the frequencies cause the stopping voltages to be different. Okay, now blue has a higher frequency, a higher energy than red. Okay, so it looks from this graph that the higher the frequency, the greater the magnitude of the stopping voltage. Okay, now that makes sense because you would need more voltage, more stopping voltage to stop the electrons that have a higher energy or higher frequency. So that kind of makes sense. Okay, but let me show you some things that maybe don't really make sense. Okay, so experimentally it was found that number one, the stopping voltage stays the same no matter what the intensity. Okay, that is kind of weird. Okay, therefore if you increase the light intensity due to more, therefore if there's an increase in light intensity due to more electrons emitted, the intensity has no effect on the kinetic energy of the electrons. Now classical physics at the time would have said that, okay, the greater the intensity, the greater the emission, and the greater the energy, and the more electrons would be emitted. But that doesn't happen, so that was really, really weird. Okay. Number two, the stopping voltage depends on the frequency of the light. Okay, that's very weird when you think about it. Okay, so in this case, the greater the frequency, the greater the stopping voltage, and I say greater here being more negative. So whenever I say greater voltage, I mean a difference, a magnitude that's greater from a greater distance from zero. Okay. And more energy means, it basically means more kinetic energy. Okay. In fact, no electrons are emitted if the frequency is below what's called the critical frequency or the threshold frequency, even if the light is very intense. Okay. Classical physics has absolutely no explanation for this. This was totally unexplained. Very, very strange stuff. Okay. And number three, electrons are emitted immediately after the light hits the surface. There is absolutely no time delay. Classical physics would say, well, a low-intensity beam should emit electrons after a time delay since less energy is involved and it takes more time for those electrons to absorb that lower energy of the photon or the electromagnetic wave. Okay? So these were unexpected, and they violate the classical laws of physics. So no matter what kind of photosurface you use, the same trends are always shown. Okay, very, very, very bizarre. Okay, so again, let's analyze it a little bit further. Okay, I have it set up right here where I have violet light being shined on a photosurface, and I've adjusted the battery such that it appears as though I have achieved my stopping voltage. Okay, which in this case is 0.92 volts. So you see these electrons that are emitted, that are shot off the surface. They come over here and they just barely don't touch that negative plate, okay? So that's what I want when I want to achieve the stopping voltage. Now, if an electron on the photosurface absorbs a photon of frequency f, its energy increases by exactly hf, okay? Now, it takes a certain amount of energy to pull an electron off an atom in the first place on the photosurface, okay? The energy of each photon equals the energy of each loosened electron, and again, we're assuming that one photon loosens one electron, and that's going to be hf, okay? The stopping voltage, that's my potential difference between the battery, that's V sub s, okay? There's an electric field created by this battery, okay? And that electric field goes from the positive plate to the negative plate, and that field is given by voltage over distance, okay? And each electron is repulsed by a force equals F equals QE, which is QVS over D. And of course, the force acts to the left in this diagram. I have not shown that force vector, okay? Now, the energy to pull an electron off the atom on the photosurface, as I said before, is really the work done, okay? So work is force through a distance, but the force is QE, so that's QED, okay? That's QV sub s over D times D. Notice how the D's cancel, and that's really Q times the voltage, and that's the maximum kinetic energy of the electrons, okay? Now I'm going to call this work done the work function. I'm going to give it a special variable, and that's called the Greek letter phi, okay? Now, if the energy is greater than phi, then the electron breaks free, okay? And its kinetic energy is now hf, which is its energy, minus the work function, okay? Minus Ke max, okay? And that's going to be hf minus phi equals qv sub s. So you might want to pause this particular slide and really sort of look at my rationale, my mathematical rationale of how I get to this statement. This is a very, very important algebraic statement that we're going to use a lot, okay? Notice also that the current in this circuit is 0, okay? Okay, remember the question we posed, okay? So why is intensity proportional to current, okay? We said that this can either be due to more electrons being emitted or electrons moving faster from the surface when light is bright, and I told you that case number 1 is true, okay? Well, a simpler way of remembering this, okay, maybe I should have shown this to you before I showed you the other way, okay? Remember intensity? Intensity is power per unit area. It's a watt per square meter, okay? Well, power is an energy per unit time. So intensity is energy over time, all over area, okay? Energy per unit time, well, energy of a photon is hf. If you have an n number of photons, you have nhf as your total energy. So energy over time over area becomes nhf over t times a, okay? So what have I shown here? Well, I've shown that n is proportional to the intensity, okay? So again, it's because the intensity is proportional to current because more electrons are being emitted when light is bright, not because they're moving faster. There's no velocity or speed variable in any of these equations, and mainly it's because we've quantized the energy of a photon to be E equals hf, okay? Not E equals 1/2 mv squared. So the v is gone, okay? Now, here's my equation that I told you was very important before. Note that this is of the form y equals mx plus b, which should remind you of a linear graph. Okay, so when we graph kinetic energy against F, we get linear graphs, okay, where the y-intercept is not 0. Okay, so these are not directly proportional. Okay, and it turns out that the slopes of different photosurfaces are the same, okay, but their y-intercepts are different. Now check it out. These are linear functions. The y-intercept is the negative of the work function, and the work function is characteristic of the particular surface, as you can see here. So for example, zinc and platinum would have different y-intercepts if you were to graph the data, okay? The gradient is actually Planck's constant. The gradient of these lines is Planck's constant, and Planck's constant is the same no matter what the type of photosurface. The x-intercept is what's called the critical or threshold frequency. You see it written F sub c or usually F naught, I guess. And different surfaces have different characteristics and work functions. Now, note that from this equation I can rearrange it like this, where V sub s is hf over q minus phi over q, okay, which means in that case, if you were to graph the stopping voltage against F, it's still a straight line, but the slope is h over q in that case, and the intercept is negative phi over q. Okay. Note also that phi is hf naught, and hf naught, which is the energy of a photon at its critical or threshold frequency, is hc over lambda naught. So we could also characterize the threshold frequency by the threshold wavelength, which is lambda naught. Okay. You getting all this? All right. Let's do a couple of examples. Okay. Go ahead and read this example. Pretty simple one. Okay, so a photoemissive surface has a threshold wavelength as given. Calculate its threshold frequency. Well, that's pretty straightforward. Again, hf naught is hc over lambda naught, and I got 4.6 times 10 to the 14 hertz. Okay, its work function, I got 1.9 electron volts. All right. So again, the work function is hf naught. Okay, and remember how I said the work function is characteristic of the substance used? Well, every substance also has its own particular critical frequency that's different than another substance, another photoemissive surface. Okay, the maximum speed of the electrons emitted by violet light of 400 nanometers, which is what I have here shown in this diagram. Okay, here I'm gonna equate kinetic energy to the energy of the photon. Okay. And that's okay, I can do that because electrons have mass and photons don't. And when I do that, I end up rearranging and solving for V, and I get 6.4 times 10 to the 5th meters per second, which is pretty darn fast. Okay, try this example. Okay, so now I have monochromatic light, so that's light of all one color. Okay, 400 nanometers. Falling on a surface of critical frequency, and now we're being told that it releases 10 to the 10th electrons per second. What's the current collected? Okay, well, it's 10 to the 10 times the charge on one electron, which is 1.6 times 10 to the minus 9 amperes. If the intensities increase, what will the current be? It will double, because I've been telling you and I've proven to you that the intensity is proportional to the current. If you double one, you double the other. If this doubled intensity falls on the photosurface, what will the current be? Okay, well, turns out that the current will be 0. Okay, and this is the kind of IB question where they kind of try to trick you. You want to always compare the wavelength of the light or frequency of the light given in a problem to the critical wavelength or frequency. And if it's less than the critical frequency, okay, you're not going to get any current at all. So these types of questions are actually quite common in IB paper questions.